In this video, I'll show you how you can solve problems for a random variable with a gamma distribution. In a certain city, the daily consumption of electric power in millions of kilowatt hours is a random variable with x having a gamma distribution with an average of 6 and a variance of 12. So what this means is that our expected value, which is equal to our average, is equal to 6, and our variance, which is equal to sigma squared, is equal to 12. Well, because we know that this is a gamma distribution, we happen to know that the average, the expected value, is equal to alpha times beta, and this is equal to 6. And so this variance is then equal to alpha times beta squared, which in this case is equal to 12. So now we have two equations and we have two unknowns. So we can solve for one of the variables in one of the equations. So let's first solve for alpha in this equation. This is equal to alpha equal to 6 over beta. And if we plug alpha into this problem over here, then we get 6 over beta times beta squared, which is equal to 6 beta. This is then equal to 12, so 6 beta is equal to 12. So if we divide by 6 on both sides, we get that beta is equal to 2. Now if we plug this back in over here, we find that alpha is equal to 6 over 2, which is equal to 3. So alpha is equal to 3 and beta is equal to 2. All right, so now what is the probability the number of kilowatt hours is between 4 and 6? We can find this by integrating our probability density function. So the general form of the probability density function for a gamma distribution is 1 over beta to the alpha, the gamma function of alpha, x to the alpha minus 1, e to the negative x over beta. So since we know alpha and beta, we can plug these into our equation to get the gamma PDF. So this is 1 over 2 cubed gamma of 3, x to the second power, because that's 3 minus 1, e to the negative x over 2. This will be our probability density function when x is greater than 0. Well, the first thing we notice about this is that integrating this will be a little bit difficult because we're going to have to be doing integration by parts. So let's set up the integration. So this would be from 4 to 8. So to find the probability, we do the same thing that we've done in most problems. We integrate over the space that we're interested in. So from 4 to 8 of our probability density function, gamma of 3, x to the second, e to the negative x over 2 dx. Well, to solve this, we're going to have to do integration by parts. And so that's completely doable, but we're not going to do it in this example. We're going to use our software R instead to solve this problem. So let's go on over to R. So again, our alpha is equal to 3 and beta is equal to 2. We can use the function p gamma to find the probability that we're interested in. So here, if we highlight and run our alpha, so if we define alpha and beta, and we don't necessarily have to do this, we could just put in 3 and 1 over 2 here, but I think this helps with just kind of, if we're going to be doing multiple commands, keeping things straight. And so p gamma will give of 8 alpha comma 1 over beta will give me the probability that the kilowatt hours will be less than 8. So again, this first function is essentially just the probability that x is less than 8. And to find the probability that it's between 4 and 8, that means that I then have to subtract off the area that falls below 4. So that's x less than 4. And that is what then this function is. So if I run this, then I get the area between 4 and 8 in a gamma distribution with an alpha of 3 and a beta of 2. And that is 0.4385731. So if you decide to solve for this integration, you should get the same value as we did in R. So now moving back to our last problem, it says, given a month has 31 days, how many kilowatt hours should we expect the city to consume during a month? So again, our variable is in respect to days, but we now want to know how many kilowatt hours will be in 31 days or in 1 month. And so we can use the rules for linear combinations, because y would be then the number of kilowatt hours in a month. And so y is equal to 31x, and because this is a linear combination, then if we want to find the expectation of y, or the average number of kilowatt hours used in a month, we do the expectation of y, which is equal to the expectation of 31x, which is equal to then 31 times the expectation of x, according to the linear combination rules. And then this is simply equal to 31 times, if we look back up here, what was the expectation of x? 6. So 31 times 6, which is simply just equal to 186 hours. So that's how many hours we would expect in a month with 31 days. Hopefully this video helped you understand how you can solve problems for a gamma distribution.